Hello, everyone. My name is Maurizio Palesi, and it's a very pleasure for me to welcome you all in this third webinar of the Circle webinar series, which is part of the communication and dissemination activities of the QUADRATURE project. So the main purpose of the Circle webinar series is to foster knowledge exchange and bring researchers together to discuss on topics related to the area of quantum computing. And for today's session, I'm very glad to host Professor Margaret Martonosi from Princeton University, who will give a talk entitled Mind the Gap, Challenges and Opportunities in Closing the Algorithms to Device Gap in Quantum Computing. So before to introducing the speaker, let me give the floor to Professor Carmina Almodevar, who is the coordinator of the QUADRATURE project.
Yeah, thank you very much, Mauricio. Very good afternoon to everyone. And thank you, Margaret, for having invited our invitation to give a talk today in this seminar series within the QUADRATURE project. So as Mauricio just mentioned, I'm Carmina Almodevar, the coordinator of QUADRATURE, which is an European ESC Pathfinder project. So this project started almost 3 years ago, and the aim is to explore the feasibility of architectures that are composed by multiple chips to scale up quantum computing devices. And this is done with a networking package, which has a dual character and includes a quantum coherent link for transmitting quantum information between the different quantum cores and a wireless network for synchronizing and orchestrating those transfers between the different quantum cores, and all of that at cryogenic temperatures. One of the novelties of this project is not only the use of these modular architectures for the scaling up quantum computer systems, but that we do it from a full stack perspective. In other words, we go from quantum algorithms down to the quantum technology and quantum processors. And for that, we have a consortium that consists of 9 partners, like UCD Dublin in Ireland, Equal One also in Ireland, and University of Siegen in Germany, which work on the development on the quantum processors based on silicon spin qubit and also on the cavity for transmitting quantum information between them. Then we have TU Delft in the Netherlands and EPFL in Switzerland, who work on the transceiver for the wireless communication network. Then University of Catania and Technical University of Catalonia in Italy and in Spain that work on the protocols for the classical communication network. And last, Barcelona Supercomputing Center in Catalonia and Technical University of Valencia in Spain, both which we work on the compilation techniques and algorithms and more architectural aspects of this system. So that's all from my side. Thanks again, Margaret, for being here today, and I hope that you'll enjoy the talk. Thank you.
Okay, let me add a few words about how to stay tuned with QUADRATURE. I like to ask you all the tendency to visit the website of the QUADRATURE projects to follow the news of QUADRATURE in our LinkedIn page, and also to subscribe our YouTube channel, where you will find all the multimedia material related to QUADRATURE, along with the recording of these webinars. Now, let me introduce our speaker. I know that Margaret does not need any introduction because she is very known to our community, but just let me briefly introduce her. So Margaret Martonosi is the W.M. Eddy 82 University Professor at Princeton University, where she has been on the faculty since 1994. Her research area is computer architecture, with contributions to both classical and quantum hardware and software systems. Professor Martonosi is an elected member of the U.S. National Academy of Engineering and the American Academy of Arts and Sciences. In 2021, she received Computer Architecture's highest honor, the ACM IEEE Eckert-Mauchly Award, for contributions to the design, modeling, and verifications of power-efficient computer architecture. She is fellow at IEEE and ACM. Her papers have received numerous long-term impacts awards in SIG Arc, SIG Mobile, and other communities. She received a 2023 ACM Francis Allen Award for outstanding mentoring for her impacts on computer architecture and the broader computing community. So thank you very much again, Margaret, and the floor is yours.
Thanks so much for the chance to talk today. Good afternoon to you in Europe. Good morning to me here in New Jersey. I'm happy to talk about what I see as being kind of next in quantum computer architecture and systems. And the talk I give is actually going to span work over nearly 20 years now. And so it represents the work of many collaborators from my own research group and elsewhere. And with that, let's go. And also, given, the type of group and the size of group, if you want to come off mute and ask questions in the middle of this, that's fine with me. The way my screen is set up, I can't see hands being raised. So I'm fine with people just kind of popping out and asking questions themselves, and we'll see how this goes. So the way I view the quantum computing landscape is to think about it in terms of an analogy to the classical computing landscape. And if you think about the classical computing landscape, let's think about 1950 in classical computing. So in 1950 in classical computing, we had some number of computing devices that existed. They were built out of vacuum tubes and or relay circuits. The transistor had been invented in 1950, but no transistorized computer had been built yet. The other thing about 1950 is that, there were these implementations down low, and you could program them using assembly language, but there was kind of nothing of the kinds of layers we now rely on for sort of classical computing to have scale. So there's no notion of computer architecture yet, no notion of compilers, no notion of operating systems, not even really good high-level languages yet. And yet also in 1950, and this always blows my mind to think about, 1950 is when Alan Turing wrote the paper in which the first sentence asks the question, can machines think? And he sort of ideated about how machine learning essentially might occur, how machines might learn and think. And it's sort of astonishing to think that there in 1950, when machines could barely multiply, Alan Turing was thinking of this capability that they might have that was well beyond what current systems could do. So the notion of a gap from algorithms to machines was very much a part of 1950s classical computing. The last thing I'll say in this analogy is about the quote unquote winning technology. Often when it comes to quantum, we're often asked, do you think, superconducting qubits will win, or a neutral atom or whatever? I like to point out that if it was 1950 and you were asked to pick a winning technology for classical computing, you wouldn't have picked transistors. They weren't building computers out of it yet. You might have picked vacuum tubes or relay circuits. And so it is perfectly fine, in my view, to think about a world in which the winning technology, quote unquote, might change over the years, and to think about a world in which the algorithm's vision far exceeds the capabilities of the current machines, and have confidence that we can figure out how to scale it. And so, as we know, the stack in the middle is kind of how we manage to mitigate complexity to scale classical computers. And so quantum systems today have very many of these elements of the same story. There's qubit implementations down low. People are testing out different technologies that have different attributes. There's algorithms way up high, like Shor's algorithm and so forth, that far exceed the capabilities of those underlying implementations. So there's a big gap, a resource gap. And then the other gap is sort of a functionality gap. We haven't yet decided on what's the best way to fill in the box between algorithms and qubit implementations in quantum, although many people have been working on it now for many years. So my timeline for quantum looks like this. In 2003, I went to get a cup of coffee from our lounge here on campus, and my colleague, Steve Lyon, was also waiting for the same pot of coffee to brew. And in the time that it took for a pot of coffee to brew, he had pitched to me his idea for a particular qubit technology and his thoughts on what were some of the architectural issues that would actually need to be studied in order to make that qubit technology practical. And that led us to actually co-advising a PhD student. It led me down the path of acquiring some federal funding for architecting these electron spins on helium systems that he was pitching. And it led to our first ISCA paper on quantum, which was also one of the first ISCA papers on quantum, which is now, and it kind of blows my mind to think about it, nearly 20 years old. We also were part of a large team that did some of the early resource estimation, that is counting the number of qubits that different algorithms would require. And then moved into the NISQ era, noisy intermediate scale quantum, where one of my PhD students led the development of one of the early compilers for quantum computing. He's now at IBM doing, having done a lot of the work to make Qiskit as big and broad as it is, and sort of pushing through this NISQ era of trying to architect systems at scale. What we've entered most recently is kind of after NISQ, thinking about fault-tolerant quantum computing. And a lot of what I'll talk about is this sort of lessons learned from the dawn and then moving into FTQC in this talk. And so in particular, sort of a set of early lessons on quantum architecture, set of recent lessons on modularity and abstraction, and then moving into kind of real world QEC. So in sort of preparing for this talk, I took a trip in the Wayback Machine, and I actually looked at what that ISCA paper from 2007 said. And it's often a little bit cringeworthy to go back and look at papers of your own that are that old, because you sort of can't imagine what you were thinking sometimes. But in this case, I was kind of heartened by what we were thinking, because it was nice to see that we were out ahead on certain issues. So the idea of electron spins on helium is that you have electrons that are in a vacuum. They are hovering above a layer of liquid helium. And then there's silicon CCD motion control underneath that liquid helium layer. And so a voltage in a particular place can hold an electron stationary. But then if you take that positive voltage and you move it across the CCD, you can get the electron to move. So, electron spins on helium were not then a leading technology. They are not now a leading technology, but they have attributes that actually are not dissimilar from, say, neutral atoms. The notion of being able to have highly mobile qubits. They can sort of move around on this liquid helium layer, and the notion of being able to move many qubits in parallel. So what we did was actually sort of envision these buses where many qubits could be moved back and forth. And if you look at the figure on the upper right, actually the way we envisioned it was that the qubits would be stepped towards an operating zone, which is shown here in green. When they're in the operating zone, you can do 2-qubit gates on them using pulses, and then you can scramble them to move them elsewhere. Because of the nature of this technology, the operating time, the gate time, if you will, was going to be quite slow, and the movement speed was going to be quite fast. And so we had a notion of a pipeline where the execute was quite long, that the fetch and the store, that is the moving of the qubits around, could be fast. And then the idea was to take this very long operation time and make it as parallel as possible. So do as many parallel qubit operations at once in order to amortize the cost of how long it took. So this is a cycle. What you can see is that we've gone from kind of a pretty low level notion of electrons and helium to now something that looks fairly architectural and pipelinable. And indeed, the student who worked on this 20 years ago built a compiler to orchestrate the movement and the operations for these kinds of qubits in order to vectorize and highly parallelize this execution region. So slow operations, but many of them happening at once. And a lot of this ends up looking like neutral atom today, slower gate speeds than superconducting, but the ability now with neutral atoms through optical tweezers to move many electrons at once. So we were on to something in terms of not just this particular technology, but in terms of being able to think about these things architecturally and with compilers. So from then to now to the future, this notion of kind of what aspects of architecture and coordination are portable across technologies, that remains true to me as well today. So like, how can we build a compiler that will be good across multiple technologies? What are the control systems and the pulse controls that will be good across multiple technologies? And then what aspects of compilation really do need to be tailored to implementation? Where do we need to worry about crosstalk or coordination in a way that's very specific to the technology? So that's my trip in the Wayback Machine almost 20 years ago now. Over the years since then, my group did a set of work on quantum compilation and optimization. And I consider this to be kind of chapter one of our version of the NISC era. And you can see some of the papers that were part of this chapter one. I'm going to go into detail about just one of them. And the reason why I picked this one is because it was, again, an example of being able to take something that looks awfully physicsy at first and translate it to something that actually can be expressed in a way that's very architectural. So the idea here is to think about instruction set design for quantum computers. And in particular, what we were seeing, 5, 6, 7 years ago when we started this work, what we were seeing was different implementations of quantum computers were offering very different gate sets to the upper level parts of the system. And those gate sets often deeply affected the instruction count of a quantum program that you would get, and also the fidelity. Like if you were promising many, many, many gates, then the fidelity of some of those gates might be quite low. If you were promising many, many gates, then the calibration time to be able to keep all those gates in calibration with decent fidelity was very high. This work actually came about because one of my students did an internship in a company. And when he came back, he was just struck by the fact that about a third of their uptime, so like 8 hours of every 24-hour day, was spent on calibration rather than on actually executing useful programs. And so what we did in this work was we tried to say, maybe we don't need so many gates, and if we reduce the number of gates, maybe we will reduce the calibration time. What's the cost to us of reducing the number of instruction options that you have, the number of gate options that you have? And this is fully analogous to the RISC versus CISC conversations that happened in classical computer architecture 40 years ago. So basically, can we have fewer, simpler gates and get most of the benefits? That was the question. And so digging in a little bit more detail, if you sort of go back to the time that we did this study, IBM was exposing a fairly simple type of 2-qubit gate, as were Google's systems. But there were other systems that were actually exposing continuous 2-qubit gates. So the theta in these gates could take on literally any value. So it was a family of gates that needed to be calibrated for a continuous possible set of operations. It was very difficult to calibrate, even though it was very expressive and led to low instruction counts. And so, this is the classic RISC versus CISC. Can we get most of the benefit out of these kinds of gates and use very few of these kind of gates, or maybe pick particular thetas to focus on to reduce calibration overhead while retaining enough expressivity? And the answer is, just like most RISC versus CISC kinds of arguments, the answer is yes. So what we did was we looked at a family of possible gates with different I-swap angles, theta, and different C-phase angles, phi. And we said, imagine this full space is giving all the possible options to the compiler. For different kind of test programs, what's the average 2-qubit gate count that is required when you offer these different gates? And so lighter means fewer gates, which is good. Darker means more gates, which is bad. And so there are sort of opportunity spots where you can select gates that will give you low gate counts, and then you can look at their fidelity as well. And so basically, we limited ourselves to the gates that you can see in the green boxes. And then we said, actually, from those 8 gates, maybe we can drop to 7, 6, 5, or 4. What we found was that using this very constrained set of gate types offered about a 2x improvement compared to only giving people one gate type. So 4 to 8 is better than 1. But at the same time, it's nearly optimal in terms of fidelity compared to the fully continuous. So basically, it's the 90-10 rule. You don't need fully continuous gates, but 4 to 8 will typically do it for you. And then the trade-off in calibration time. This number of gates does require more calibration time than the single gate type, but it's still practical. And it's about 2 orders of magnitude less overhead than if you try to calibrate the full space of gates. So the paper basically established this notion of a 90-10 rule for gate sets in quantum computing. The actual choice of gates continues to evolve, but the notion of sort of considering calibration time as part of the gate set, I think it will be one of the enduring aspects of this work. So as we sort of transitioned into the 2020s, it was clear, I think, to many of us that we wanted to think about modularity, and clearly that's important to your work in Quadrature as well. I'll just give one example of that out of our work. I have found when I've presented this slide that this is an age gap, a generation gap slide. So the idea that we are shooting for with our modularity work was we wanted to come up with the ability to be somewhat specialized in terms of modules that we could offer as little QPUs or modules within a QPU to improve the mapping from application to hardware. But as you saw in the gate set example, unconstrained specialization can be worse than just having a sea of qubits. Okay, so we want to balance heterogeneity and modularity, and we want to use modularity to be able to scale things. So what is this picture on the right-hand side of this slide? This was the revolutionary textbook. Excuse me? So this picture on the right-hand side was Mead and Conway's VLSI systems textbook from late 1970s, early 1980s. Mead and Conway introduced a way of designing VLSI systems that was parameterized, that would move from technology to technology. Everything about the Mead and Conway approach revolutionized VLSI design and allowed it to move into the era of electronic design automation with sort of lambda rules and so forth. And if you're my age, this was a big deal. What I'm learning when I present this slide is that if you are less than my age, you've probably never seen this textbook before, but I'd encourage you to Google Mead and Conway. It's an amazing story. Okay, so we're trying to come up with a Mead and Conway for quantum. And in particular, our work on HEADARC basically said, let's not force ourselves to always think about qubits as representing a particular technology. Let's think about qubits as modules that can be built into registers, that can be built into, say, a unit like entanglement distillation. And let's come up with design rules kind of like Mead and Conway had this notion of lambda parameters. Let's come up with design rules that will give us some constraints on how we can manipulate these different modules and standard cells, while still mostly keeping the abstraction of not needing to look inside of them. So, for example, you might have compute qubits and storage qubits. There was a point when people were thinking, superconducting qubits with surface codes for compute and neutral atom qubits with QLDPC codes for storage. Whether or not you agree with that technology choice, you can sort of wrap them up inside these modules and sort of shift through different technology eras without needing to unpack that in detail. So it's the idea of having modules and then having design rules that allow you to systematically use those modules and to simulate within them at higher speeds. So this is a whole lot of detail, but here's an example of a whole bunch of different superconducting qubits with different attributes. I'm not going to go into detail, but the point of it is you need not go into detail. You can use these sort of notions of abstract computer storage qubits as wrappers around these more detailed characteristics and only simulate the detailed characteristics when you need to dig in. When you don't need to dig into that, you can stay with higher level design rules like compute qubits can be connected to at most 4 other qubits and so forth. So we actually use this notion of multi-level modular abstractions to show how to project performance and optimize performance without going down to full device level simulation all the time. We demonstrate on things like code teleportation in the paper. And our next step is that we've recently been selected for funding from the US DARPA agency to do a heterogeneous architectural study for quantum called HARC, where each module, each tile can be heterogeneous either in qubit technology or in error correction choices, and we can compose together tiles. So I really hope that we can keep the lines of communication between Quadrature and our work open as we kind of take our next steps, starting that HARC project. So with that, so some of you might know, I actually spent 4 years on leave from Princeton, not completely away from research, but somewhat away from research while I led the computing directorate at the US National Science Foundation. That was a very rewarding thing. When I came back from it and started to dig into research again, I felt like to some degree the world had changed because I left during the NISQ year and I came back with this full-on quantum error correction era. And really, it's been a challenge to sort of recognize the degree to which quantum error correction is the thing to study right now. And so this sort of real-world QEC part of the arrow is where we are right now in my group, focusing on how we need to architect for quantum error correction. So with that, I'm going to talk about some of the newest work that I've been involved in. This is a collaboration between Josh Vishly and Fred Chong at the University of Chicago, and Satvik and Swamit at University of Wisconsin, and myself at Princeton. And it was just presented at the ASPLOS conference last week. And so the idea here is the following. When you do error correcting codes, one of the things that has to happen on the QPU, as you know, is you need to have the QPU set up to do syndrome measurement, to measure attributes of the ancilla bits and send those attributes over to a classical decoding unit that will say, when I see this syndrome measurement, I diagnose it as this error occurred. And so there's this back and forth of syndrome measurement on the QPU side and diagnosis or decode on the classical side. Here's the thing. Syndrome measurement circuits, so quantum error correction is at one level, and people implement it in terms of syndrome measurement circuits. If you've done your analysis of your QEC code at the sort of theoretical level, it is possible that the underlying syndrome measurement circuit won't give you the same code distance, the same degree of protection that the theory said it would. So different ways of implementing the syndrome measurement can give you higher or lower code distance. That's one issue. Second issue is that different ways of doing the syndrome measurement can actually lead to ambiguities. You measure the syndrome, you send it to the decoder, and it says, actually, there are 2 or 3 or more different errors that might have caused this syndrome, and we need to deduce which of those errors actually occurred. The typical decoder today will simply guess the most likely error, and if there are second or ambiguous errors, it will never diagnose that. So what we want to do in prop hunt is to, first of all, optimize syndrome circuits so that they offer, as much as possible, the full code distance that the theory provided. And second of all, we want to optimize syndrome circuits such that they eliminate possibilities for ambiguity. So when a syndrome is measured, there's really only one answer that the decoder can give for what error occurred. So this is a very busy figure, but the idea is to go from the syndrome measurement circuit to finding ambiguities, to using a MaxSat solver to reduce the number of ambiguities, apply these changes, and have a better syndrome measurement circuit than we otherwise would. So when we move into the world of QEC, we move from sort of a single logical qubit into these patches that represent both the data qubits and the ancilla qubits for, in this case, the surface code. And the syndrome measurement circuit is a set of X-check and Z-check circuits, in this case, that together are going to get them the syndrome data that needs to get sent from the QPU over to the classical decoding unit. So basically, this is the theory, this red and blue set of patches, and then these are the underlying circuits. But there's different ways that we could schedule these circuits, and actually, depending on the order in which we execute these CNOTs, it looks innocent enough, but depending on the order in which we execute these CNOTs, we can get orders of magnitude difference in the logical error rate that this error correcting code actually achieves. Literally orders of magnitude difference from a poor schedule to a good schedule. In this graph, lower is better. Lower error rates are better, obviously, and this is powers of 10 on the y-axis. So what we want to do is basically be able to change the gate scheduling to automate the process of finding the good schedules. Now, it turns out if you are kind of a QEC wizard, then you can sit down, you can stare at one of these patches, and you can decide what the good schedule is. But as we move out to higher code distances, as we move out to different codes, as we consider defects in the fabric, the notion of how to find a good schedule gets harder and harder and harder. So what we want to do is to be able to automate that. So this is a little bit more on the notion of ambiguity. So that's when different error constellations can lead to the same circuit level measurement. What we want to do is avoid that ambiguity by changing the order in which things occur. And what we want to do in our work is sort of automate using SAT solvers, the process of finding these ambiguous errors in the error matrix and avoiding them entirely. And so what prop hunt does is it looks at these as sort of local subproblems to be fixed. If that's a circuit level model, you can always think about QEC decode in terms of a graph. So you want to find subproblems with ambiguity, find a minimum set of gate errors, and then do literally local tweaks, almost like a genetic algorithm, or using a SAT solver itself, do local tweaks to change the order. you can see the different orders portrayed here until you get one that actually reduces the ambiguities present. And you're sort of iteratively improving and checking whether you've improved the ambiguity level. So what we did was we took a set of different codes, some surface codes, but also other codes that you can see here with different distances represented. And across all of them, we can see that we're getting better, we're getting improved behaviors. The prop hunt is the starred line here, improved behaviors across a range of different code benchmarks. The hand design circuit, you can see, is the square. And so where a hand design circuit existed, for example, in this top row, then prop hunt is meeting the hand design circuit. So basically that wizard, it's often Craig Gigney, the wizard has figured out what is an optimal circuit and laid it out, and we're able to automate the process of matching it. But there are other circuits for which no wizard has yet hand designed the perfect decoder. And for those, we can see that prop hunt is offering improvements over the sort of initial optimization start. So you can consider it to seed your thinking about what the wizard would want to do in a hand design or avoid the hand design entirely. Okay, and so basically this lets you find better schedules, and it actually gets you on the order of 2 to 4x improvement in logical error rate, which is huge. You know, every order of magnitude that you can get in logical error rate is a huge benefit, either in improving the fidelity of the runs on your quantum computer or reducing the number of qubits that you need. If you have a better logical error rate, maybe you can use a smaller code distance with fewer qubits and get the same kind of protection. So that's my tour of some of the stuff we've been working on. I'll end where I started, namely with this notion of an analogy to classical computing. On the quantum side, I don't think we've really solidified how the layers will work, but we do have a pretty good notion of what are some of the to-do items between algorithms and qubit implementations. And there's always been, I think, a strong and now increasingly strong need for architects and systems folks to come in and work on this, because one of the things that's really clear is the notion of what you can do with a hand design when you have a handful of qubits is very different from what you can do when you're talking about thousands or millions of qubits. When you're moving out to scale, you need to have a toolkit that accommodates different levels of abstraction and modularity. And the reality is that classical computing has been navigating those notions of abstraction and modularity for decades now. And it would be crazy not to consider aspects of the classical toolkit when we think about the quantum toolkit. So with that, I think I'm going to end on this slide, and thank you for your attention. And I'm going to stop sharing in case if people have questions, I can actually see your faces. So I'm going to stop sharing now. Thanks very much.
Thank you very much, Margaret. Any questions from the audience?
Yes, hello, I have a question.
Yes, please.
Hi, Margaret. I'm Pau. So basically, I have a question when you were talking about the gate set. So I guess that back then, the optimal gate set consists, well, it depends on the application that you're trying to run. But now in an error-corrected system, the available logical gates that you can execute is constrained by the error correction code that you're using. So I would ask, does it make sense to optimize the gate set not based on the application that you want to execute, but based on the quantum error correction code that you're using? And then this would result into a application agnostic design?
So that's a good question. I think so. One question is, like, now that we're sort of focused so much on FTQC in quantum error correction, should we redo the gate set analysis with error correction in mind? And I think almost certainly yes to that part. I would say that when I think back to the gate set optimization paper from whatever that was 5 years ago, it didn't end up being particularly application tailored. The gates that worked well across most. That study was really a recognition that you didn't need these continuous theta and phi gates. So I think that part wasn't particularly application tailored, but I 100% agree with your sense that if we're moving into an error-corrected world, then we need to rethink what we think about as our gate set going forward. And so I'm knowing what you work on, Pao, I am assuming that you can appreciate that maybe transversal gates would be a key thing to study. And certainly our previous work, because it was in a NISC era, didn't think about transversal gate operations. Thanks.
Yeah, that's what I was going to. Thank you.
Other questions? Yes, Carmen.
Yeah, thank you very much, Margaret, for your talk, splendid as usual. And thank you for sharing your trip on quantum computing and bringing us 20 years ago, almost to the prehistory, I would say, of quantum computing. That was not prehistory. That was very nice. So, yeah, I have a more, let's say, philosophical questions. As you know, it will be silly not to apply the concepts of the thing that we have learned for classical computing to quantum computing, right? We have all that background that we can, we are going through the similar problems. But at the same time, I mean that also we are biased by that knowledge, I will say, right? So, I mean, at least that's the impression I have sometimes, that it's good that we have that background, right, and that knowledge, but at the same time it's bad because it's more difficult to think out of the box, and quantum computing and quantum physics and mechanics is completely different from classical, right? So I would like to hear your opinion about that, right? So if it's good to really apply those concepts or not, or some of them might be good, or maybe we are missing something, or we are, restricting ourselves because we are thinking in that way, yeah?
Oh, that's a fascinating question. It could be. So I would say when I think about the state of quantum implementations today, there's a heavy focus from the sort of physics and material science community and so forth. And they bring one set of out-of-the-box ideas and so forth. And so if anything, when I think about the conversations I've had with my colleagues who are more on the qubit implementation side of the spectrum, I feel like our classical ideas are out-of-the-box ideas for them, because that's not how they think about the world. And so I feel like even though they are sort of time-honored techniques for classical architects, they are out of the box for quantum. So on that sense, I can sort of defend pulling things out of that toolkit. On the other hand, it's true that not all of them are going to work the same way. And so there needs to be kind of other flows of information in as well. For example, I think a lot of the architectural ideas seem to have some legs, the notion of parallelism, vectorization, and so forth. But I don't know that anyone's really come up with decent programming languages for quantum. I hope I'm not offending anyone here. So I think there's still a lot of work to be done in terms of getting from, when I read a quantum algorithms paper, it's like it's reading math. It's like linear algebra. And I don't think anything we've done in the programming languages part of the space has really helped with that part of the mapping. And so I don't think there's good tools in the toolkit yet for that. And we need more algorithms for sure for quantum computing to be useful. So that's a place where there is yet some other set of out-of-the-box thoughts that need to come in and that haven't yet.
Okay, thank you.
Other questions? Okay, so I can continue with the question from Carmen. So, Margaret, if you were advising a computer architecture researcher on how to transition into this quantum computing world, which areas would you recommend they focus on to make the most of their expertise?
Let's see. So I think one thing that's been really fascinating to me is this interplay between the quantum processing unit and the classical QEC decode. So this interplay of the quantum processor needing to do syndrome measurement and then send it over for classical decode. I think there is a world of opportunities there, and many of them haven't really scratched the surface yet. So it's true that you need to understand quantum error correction, and that's not the easiest lift in the world to start with. But the notions of latency tolerance and latency reduction between the QPU and the CPU or GPU or whatever is the decoder, that I think has a lot of familiarity to classical computer architects. And it's a place, I think, where there's a lot of opportunities for classical architecture to show value in mitigating those latencies and letting the quantum side go at its full speed. So that's one place. Another place I think would be in the continuing some of the mapping, call it compilation, but it's really more like FPGA mapping onto different qubit implementations, and in particular, doing that with increasing degrees of abstraction. We aren't going to be able to scale to 1 million qubits if we're really orchestrating individual qubits one at a time. We need some notion of blocks, of modules, and so forth. And figuring out how to do that in ways that sort of bring in all that we've learned from the classical side, but also acknowledge the differences that, like, when quantum modules want to interact, the transduction that's required to go from one module to another is harder. So my group worked on circuit cutting for quite a while. Quantum circuit cutting is very intuitive to a classical architect because we do it on FPGAs in classical all the time, right? We take a big circuit, we cut it into pieces, and we run it one at a time on the FPGA, and we sew it back together again. In the classical world, that's very intuitive. In the quantum world, each of those sewing it back together again has an exponential cost. And so one of the things that I find fascinating about being a classical architect in a quantum world is these moments where your intuition leads you a little bit astray until you learn a little bit more. And so, I still believe in circuit cutting being useful in quantum systems, but it isn't sort of an out-of-the-box instant win. You have to think about how to mitigate that exponential cost when you're sewing things back together, the exponential reconstruction cost. And so it's this mix of like, there are interesting opportunities around modularity, around scale. And yet, if you lean too hard on your classical intuition, it doesn't work.
Thank you very much. Other questions? Yes, Rodrigo?
Yes. Thank you for the talk. It was very nice, firstly. And also, I think my question is in the same line as Pau asked before about transversal gates and the gates that are allowed for QEC codes. And I've seen the work you've done in these two qubit gates like continuous phase, and how this increases the expressivity, right, of the operations you can do. Of course, you can always decompose them into discrete sets that are I don't know how to say, allowed for the QEC codes. But there are also these other algorithms, like, for example, variational algorithms that do require these angles. So do you think this is like a content part that maybe will not allow these algorithms to scale, or do you think that the conversion might not kill it?
I think if you really believe that you have an algorithm that requires particular angles in order to scale, then you could imagine having a tailored gate set that selects angles specifically for that algorithm, calibrates specifically for that algorithm, and then runs. And so that actually brings me to another one of those classical meets quantum moments, which is that most QPUs, most quantum processors have, an underlying pulse control unit that is basically dictating the behavior of these gates by sending sequences of analog pulses, microwave pulses in some cases, lasers in other cases, to actually be the gate. And what was a thing for a while, but hasn't been a thing lately, at least as far as I've seen, is treating those pulses as something that can be itself programmed. To me, the pulse control unit looks a ton like microprogramming. So underlying a particular kind of software-facing gate or software-facing operation is actually a set of micro operations that together create the functionality of that software-facing gate. And so if we have the right visibility into those pulse control units and the ability to program sequences of them, then we could do more application-tailored gates. Some of that's going to be hard to do as academic researchers because gaining access to calibration data and pulse control sequences and stuff has been hard, or at least variable. For a while, IBM had their, open pulse API pretty exposed. I think they've pulled back on that now. But I do 100% believe that pulse control unit can be thought of similar to microprogramming. And then we get some of the benefits, just like, there was a point in the 1980s, 1990s where people didn't think Intel would be able to pipeline their x86 instruction set because it was too irregular and too complex, too CISC. And what they said was, we're just going to break it into micro ops and pipeline those. And so I think there is kind of a set of innovations that could happen at the pulse control level if the right researchers and innovators get decent access to that level.
Yeah, I think that's a very nice alternative to cope with this. In fact, I think like this kind of neutral atoms technology cope with this very nicely. For example, I think I don't know which company of neutral atoms, I believe Pascal. They have a nice software where you can play around with the pulse parameters, like with the amplitude and the tuning. And I think that's a very nice way to see and control things individually. So thank you again for the talk.
Well, thanks. I'll check out I'll check out the Pascal API. Thank you.
Thank you. So we have time for another short question. Okay.
I can ask another question if no one else.
Yes. Yeah.
Yeah. So, Margaret, you also mentioned about this proposal, right, that just got accepted, and in which you use a hybrid architecture, right, for quantum error correction, for both quantum error correction and the technology. So I can see what advantages could be of that architecture, but I'm not sure about what will be the main bottlenecks. I guess that the translation between the codes, between the technologies. So can you just, what do you foresee that will be the main, let's say, bottlenecks or challenges of that architecture? I think there are many, right? So
yeah, I think so too. So I will say that, like, as we were, for people who are faculty, for people who've written proposals, this is going to sound very familiar. If you haven't yet written a proposal, maybe this will be new to you, but the act of writing a proposal is often where you already start learning stuff just from the act of writing it and putting your story together, right? And so as the four of us were writing our HARC proposal, we became more and more and more convinced that heterogeneity of different quantum error correction codes could be very useful. To have a tile over here with maybe a higher code distance than another tile, or to have a tile with some parts of the system being surface codes and other parts being QLDPC. Could totally imagine that. When it came to heterogeneity of qubit technologies, I have to admit, it was hard for me to believe that we'd have like a big room with some superconducting qubits in a fridge over here, a neutral atom over here and them interacting. It seems so hard to get one system with one technology up and running that the idea of actually having heterogeneous systems in a data center tested my imagination. And that's not to say it won't happen, but it's to say it tested my imagination. And so I think some of the questions about this heterogeneity will be more from a implementation standpoint than from a mapping or architecture standpoint. But having said that, the goal is to be able to interconnect these QPUs using some photonic interconnect. And actually, there are other teams that are just focused on the photonic part, and ours and some other teams are focused on the compilation and mapping. So the idea is to be able to build up modular systems and pre-compile tiles or blocks, and then sew them together using this photonic interconnect, or at least to see when that does or doesn't help. And so to me, there's some amount of necessary modularity that we just can't build a QPU that's bigger than a certain size. So that kind of modularity will be useful. Slicing it into even smaller tiles may not be useful for all the reasons that circuit cutting has problems. Slicing something too much and then requiring extra communication or extra kind of reconstruction costs between things probably won't be good. So I think one set of research lessons might be around like how to come up with good decisions about how big the modules should be, and then how to come up with good decisions about what kinds of error correction codes to use. That's my guess now.
Okay. We'll see, right? We are looking forward to that. Okay, thank you.
Thank you. Thank you all for taking the time to join. This has been interesting and fun.
Yes, thank you again. So with this, we can conclude this webinar. We thank you again, Margaret, for your very beautiful talk. Thank you again. See you. Bye-bye.
Thank you. Thank you very much. Bye.